So in this video, I'm going to walk you through how to read a proton NMR spectrum. We're going to go through two molecules, ethyl acetate and Zolendek, which is a prescription drug. But to start with, there are four main things that we should consider when looking at NMR. First, we should look at the number of signals. This usually dictates how many different types of protons are in a molecule. So for example, if you had a methyl group, which is CH3, you would only have one signal because all three of those hydrogens are identical. They all have the same neighbors, essentially. The second thing we need to look at is the position of the signals. So depending on their position depends on what type of proton they are. So for example, our protons attached to carboxylic acids tend to be more up to the 10, 11, 12 BPM range, while amines tend to be down here in like the 1, 2 to 3 BPM range. The third thing we need to look for are the integration of each signal. So usually the computer does this for us. If we don't do it, you can see it here just by the 3H. This means that the signal in this position is representative of three different hydrogens. So it is only one signal, so we can assume that all three of these hydrogens have the same environment. They're identical hydrogens. And then finally, the fourth thing we would look at when looking at NMR is the splicing patterns or the spin patterns. So this is basically how many lanes we have per signal. So for example, for this first one here, where there's three different signals, we can assume that its neighbor will have two protons. So basically you take the number of signals and subtract by 1. So we would know that here we have 3 protons that only have 2 neighbors, our neighbors meaning protons. So it's connected, perhaps this is a CH3 connected to maybe a CH2. So that would only have 2 protons. Similarly, this next one would have 0 neighbors because it has 1 spike. So 1 minus 1 is 0. And then over here, it looks like we have 1, 2, 3, 4. So minus 1 would be 3. So it had 3 hydrogens. And basically using all this information, we can kind of piece together what the molecule would look like. So to start with, I know I kind of use this NMR as an example when explaining that, but we'll start with ethyl acetate. So if we're looking here, we see it has a ketone and an ether. It'll also have, as we can see, like 1, 2, 3 hydrogens, 4, 5, 6, 7, 8. So we know that this is only going to be one signal because all 3 of those hydrogens are identical. Again, these hydrogens will be identical, and then so will these. So we know without even looking at the NMR that there will be 3 signals. And if we scroll down, we see this is the case. For the next part, the positioning of them will give us information. So one thing I didn't mention about positioning is there's something called the de-shielding effect. So even though this is a methyl group, it is right next to a ketone, which means it's going to be slightly de-shielded because of the electronegative effects of an oxygen group. So it will be just downfield a little bit farther. So instead of at that like 0.99 BPM, it'll probably be closer to like 1 or 2 BPMs because it's next to the oxygen. Same thing for these 2 hydrogens, they'll be a little bit more de-shielded than these, this methyl group. So if we look down here, likely these 2 hydrogens, of course, we already know is this right next to that ether, but it also makes sense because it's down further near 4. So along with just ethers being in this 4 range, it's a little on the upper side of that range because it is right next to that ether. And then our next, our next molecule, this one, which is really close to 1, is probably this methyl group, just because it is the farthest away from our 2 functional groups. And then this one here, just after 2, is likely this methyl group, which is right next to that ketone. All right, and then in terms of splicing, we know that here we have 3, 1, 2, 3, so minus 1 is 2. So if we do indeed think that this signal here is this end methyl, we can look to its neighbor. and it has 2 protons. So we would assume that this is correct, as this splicing pattern shows 2 neighbors. For this next one, we decided this was probably our other methyl group. It only has 1 signal, so 1 minus 1 is 0, meaning there are no neighbors. If we look over here, we're going to find that there are no hydrogens on this ketone here. So that's likely correct. And then again, over here with our ether, it has 1, 2, 3, 4. So minus 1 is 3. So if we come over to this carbon with these 2 protons, we can see that, look, this neighbor here has 1, 2, 3 hydrogens. So this is kind of how you'd walk through an NMR to determine a molecule. So this is an easier one. Let's look up a little bit more complicated one. So this is the structure for Solandac. It's a non-steroidal anti-inflammatory drug. So this has like biological and pharmaceutical applications. So if we start with kind of our step-by-step, so the first one was always the amount of signals. So if we look down here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It looks like signals. Here, I can mark these. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that means we're going to have 10 sets of identical hydrogens. This does not give us the number of hydrogens, just simply the number of identical groups of them. So that does give us some information. However, in one like this, I do like to go to the position just because we can get a little bit more information. I am going to, let's pull up our spectra data and we'll put these side by side so we can actually see. Probably make life just a little bit easier. So we can see, first of all, we know we have our structure, so we can look at our structure. We know we have a carboxylic acid. So if we look over here, we see that carboxylic acids tend to occur around 10 to 11 ppm. And look, we see that right there. That is our carboxylic acid. So perfect. We know that that one does end up being our carboxylic acid. So we can mark that one off. If we want to look at it, make sure it is further, we see that there's only 1 peak, which means it should have 0 neighbors. And if we go up to here, this carbon here has 0 protons. So we know that that is likely correct. This proton here has 0 carbons. We don't have integration on these, however, we can still gain valuable information about the molecule. Okay, so now let's look at this set of signals. So if we look over here to our positioning again, we see that aromatic compounds tend to happen between 7 and 8, which is right about where this is. And if we look up to here, we see we have quite a few aromatic compounds. So we can attribute these, at least these 4 or 5 right here, to be in that, those aromatic compounds. All right, so then as we're working our way down, let me see, I think I missed something here. Oh no, okay, cool. So yes, all 6 of these actually would be in that, those aromatic compounds. All right, so one of our other major groups up here is this methyl group. So in that methyl group, usually we see methyls like around 1 to 2-ish. You can see over here on our chart. Usually you're provided with the spectral data, so it's okay that we're using this while looking at our molecules. And if we scroll down here, we see they're all past 2, but that would make sense because it is going to be de-shielded because it's right next to this ketone. So we can also look, it has 1 signal, so it's going to have 0 neighbors. So all these would really work. So let's see if we can narrow it down just a bit more. I guess we do also have this other methyl group here. And this methyl group is going to be less deshielded than this one because it's only next to this alkene, while this is next to a ketone. So we would expect this one here to be a little bit farther deshielded. And because it is a methyl, we want it as close to 2 as possible. So I'm going to say this one will be this carbon right, this proton, my apologies, right here. And this will be this one over here. Again, that's because this one is further deshielded, more deshielded, so it's further downfield or in a higher BPM, and this one's less deshielded because it's not, doesn't have next to a more electric negative atom. So that leaves this other one right here. And that one, so we're around 3-ish if we come over here and look for that. That molecule is likely going to be actually this right here. So this is kind of our only other major functional group besides our aromatics. We don't really look for halides on an NMR. They don't show up very well. So we're going to kind of ignore that fluorine. But this other S or carbon bond will likely be this last one to CH2. So it's going to be a little bit more deshielded, a little bit more downfield, which is why it does end up being around this 3. So yeah, that's how we analyze compounds through NMR spectra data.